Welcome friends to my YouTube channel Sommo Physics. Now yesterday's lecture I have discussed about the variation of internal energy with volume. Okay. Now in today's lecture I shall discuss about the heat capacity relations. Okay. That is heat capacity relations. Okay. So what is that? At first, here we are going to discuss about variation of CV with volume. Variation of CV with volume. Okay. Now, from Maxwell's relation, what we can write? We use Maxwell's this relation. Del S, del V temperature constant. This is equals to del P, del T volume constant. Okay. Now, we have to differentiate this relation with respect to T. Okay, we have to differentiate this relation with respect to T. So, what we get, if we differentiate this expression with respect to T, then we get this del 2S, del T, del V. This equals to del 2P, del T2 volume constant. Now simply we have to multiply it both sides by T. So T into del 2S, del T, del V. This simply we can write T into del 2P, del T2 volume constant. Okay. So what we can write? This we can write as del V of T del S del T volume constant T, and this we can write as T into del 2P del T2 volume constant. Okay. Now what is this? This is simply T del S means del Q del T volume constant means CV. So del CV del V temperature constant, this equals to T into del 2P del T2 volume constant. Okay. So this equation represents the variation of CV with volume, that is del CV by del V temperature constant. This is equal to T into del 2P del T2. Okay. So let us check what happens in case of a different gases. Okay. So let us check what happens in case of a different gases. Okay. So let us check what happens in case of a different gases. So first of all we take the ideal gas. So let us check what happens in case of an ideal gas. We all know for 1 mole ideal gas PV this equals to RT. So what will be my, so differentiate this term with respect to T keeping volume constant. So this will be R. So this will be del P del T volume constant. This equals to R by V. So what will be my del 2P del T2 volume constant? So if we do it with respect to T, then R is constant and V is also constant. So that will be simply 0. Now what would be the variation of variation of CV with volume? This is simply T into del 2P del T2 volume constant. This means T multiplied by 0, that is 0. So you see that in case of a perfect gas there is no variation of CV with volume. So for a perfect gas there is no variation of CV with volume. Okay. So for a perfect gas there is no variation of CV with volume. Okay. So let us check what happens in case of a real gas, or you can say what happens in case of a van der Waal gas. Okay, so let us check what happens in case of a van der Waal gas. Okay, now for 1 mole van der Waal gas, we can easily write P plus A by V square into V minus B, this equals to RT. So if you differentiate this term with respect to T, keeping volume constant, then this term is entirely constant. And since V is constant, this is also constant. So that you can write as del P del T volume constant, this equals to R. So what will be my del P del T volume constant? This is R by V minus B. Okay. So this is simply del 2P del T2 volume constant will be what? Here R is constant, B is van der Waal constant, and V is also constant. So this means this is 0. So what would be the result? Del CV del V at constant temperature. This means T into del 2P del T2 volume constant. This means T multiplied by 0. This is 0. Okay. So again you see that for a real, this is for real gas. Obviously you know it from this equation, van der Waal equation. Okay. So you see that for a real gas also there is no variation of CV with volume. Okay. So for a real gas there is no variation of CV with volume. Okay, so thus we see that whether the gas is perfect or real don't matter, the variation of CV with volume at constant temperature is always 0. Okay, so this is the first heat capacity relation. So we check the first heat capacity relation for both gases, whether it is perfect or real, no matter the variation of CV with volume at constant temperature is always 0. Okay, so this is the first issue. Now let us come to another relation. Okay, so the second relation is that variation of Cp with pressure. Okay, variation of Cp with pressure. Okay, so the variation of Cp with pressure, and here we use another Maxwell's relation, that is simply this del V del T pressure constant, this equals to minus del S del P temperature constant. Okay, now differentiating this term with respect to T, keeping P constant, what we get? Del 2V del T2 pressure constant, this you can write minus del 2S del T del P. So multiply T by both sides, you get T into del 2S del T del P, this equals to minus T into del 2V del T2 pressure constant. Okay, so what you can write this del P of this, you can write as T del S by del T pressure constant T, this equals to minus T del 2V del T2 P. Okay, fine. So what will be this? T del S means del Q, and del Q del T pressure constant means Cp. So you get the variation of Cp with pressure. This is the relation. Okay, so minus T into del 2V del T2 pressure constant. So this represents the variation of Cp with pressure. Okay, now let us check what happens in case of a perfect gas. Now for a perfect gas there is no variation of Cp with pressure. How we can prove it? So let's proceed. Okay, so let's proceed. So for 1 mole perfect gas we can write PV, this equals to RT. So here we have to find out del pressure constant. That means we have to differentiate this term with respect to T, keeping pressure constant. This is equal to R. So what will be my del V del T pressure constant? This is equals to R by P. So what will be del 2V del T2 pressure constant? R is already constant, and since pressure is constant, this is 0. So what will be the variation of Cp with pressure? This is simply minus T into del 2V del T2 pressure constant. That means minus T into 0, which means 0. Thus we see that for a perfect gas the variation of Cp with pressure is 0. So for perfect gas, there is no variation of Cp with pressure. Okay, so this is what up to today. Now in my next lecture I shall discuss few other heat capacity relations. Okay, so if you don't subscribe my channel, then kindly subscribe it to get latest videos on graduation physics. Okay, thank you.